We're going to be covering 7.4 into Chapter 7, and we're going to talk about atomic orbital hybridization. We're going to find that the atomic orbitals normally are not sufficient to form molecular orbitals, meaning to essentially they're not conducive for bonding between atoms. We'll actually learn a little bit more about this. I think I'll just wait a second. We're going to learn about the geometries of these orbitals. We're going to learn about sigma and pi bonds. Really, sigma bonds are kind of like a single bond, and pi bonds are like a multiple bond. I have to go a little further over this first, but that's a simple way to look at it. Let's go ahead and warm up with a little bit of review. And our first question asks us to draw Lewis structures. And beginning with carbon tetrachloride, well, this would be a normal molecule, and I say a normal molecule because by looking at this, I don't suspect resonance and I don't suspect an expanded octet. I'm going to go ahead and use my normal procedure, beginning with step 1, which is to draw in your central element. Now, those unpaired electrons are the ones that want to pair up and form bonds, so I'm going to line up those 4 chlorines, my peripheral atoms, to line up with those 4 unpaired electrons. Now, I don't have a step 3 because I don't have leftover electrons at this point, which means I don't have multiple bonds. For carbon disulfide, again, carbon's our central element. Sulfur's our peripheral element. Let me go ahead and line them up with 2 of those unpaired electrons. And now I am going to have a step 3. I have leftover electrons. I have 4 unpaired electrons, so let me bring them together to form 2 pairs. That essentially gives me a multiple bond, a double bond between each sulfur and the carbon. I think you would find that when we're done here, everybody has satisfied their octet. The chlorines have 8, the carbons have 8, the sulfurs have 8 outer electrons. In acetylene, I need to hold the 2 carbons together, so let me put them together with 1 bond. And then let me line up my 2 peripheral hydrogens, and I'm going to do so symmetrically. And now I can easily see that I'm going to have to form 2 more bonds, and both those bonds occur between those 2 carbons. So I'm left with a triple bond between the 2 carbons, and I can see 2, 4, 6, 8 electrons around each carbon and 2 electrons around each hydrogen. So everybody has been satisfied. In hydrazine, the 2 nitrogens are the central elements, and I draw them in like this. Let me bring in my 2 peripheral elements, and I see I have a leftover electron pair. Let me bring them together to form that pair between those 2 nitrogens. And then once again, we can see hydrogens have their 2 electrons to satisfy their octet, and the nitrogens have 8 outer electrons to satisfy their octet. Okay, let's draw some resonance structures, and I'm going to just jump to the answers, giving you just a few clues here. First, I would point out that we're going to start with the sulfur in the middle, and let me draw 1 oxygen on the left, 1 oxygen on the right, and 1 above the sulfur. Now, how many electron pairs are we moving around? Well, I have 6 electrons for the sulfur, 6 for each oxygen. That's 24 total electrons, which is 12 pairs. Let me put 1 of those pairs between the sulfur and each of those oxygens, so there's 3. And then on the first oxygen, I'm going to give another 3 pairs. For the second oxygen, I give 3 pairs. And for the third oxygen, I give 3 pairs. And then I look, each oxygen has 8 outer electrons, but what about that central sulfur? Well, at this point, the central sulfur would be missing 2 electrons, having 6 electrons, and so I need to bring down 1 of those unshared pairs on 1 of those oxygens to form a shared pair. So again, I would begin by putting all the electrons into pairs, put 1 pair between your central element and each of the peripheral elements, then start giving any additional electron pairs to the peripheral elements. I always give the peripheral elements the electron pairs, and then I can just look at the central element and see if it needs some extra electrons, and if it does, then we're going to bring 1 of the unshared pairs down. And once we have 1, the rest just fall into place. I hope that this is what you came up on your own. So again, I would take a moment to come up with your own answer, and then we'll see what I came up with. And here's what I came up with. Here's 1, course, here's the other. Okay, again, I recommend you come up with your own answers. Put me on pause until you're done. Okay, now that you're done, let's draw one. And I think we know what the rest are going to look like. Again, it's just a matter of which oxygen is involved with the double bond. And again, having the 3 oxygens, I hope you predicted 3 resonance structures. Just as on the sulfur trioxide, and on the nitride ion we had 2 oxygens, cluing us in there's going to be 2 resonance structures. Now there's not going to be 3 here, even though we see 3 oxygens, and the reason for that is one of those oxygens is already involved in bonding to the hydrogen. So it really isn't in a good position to form multiple bonds. And hence we have 2 resonance structures for the hydrogen carbonate ion, sometimes called the bicarbonate ion. Okay, draw Lewis structures, and here I expect expanded octets. If I ever see more than 4 peripheral atoms, I know I have an expanded octet. Okay, so silver is my central element in sulfur hexafluoride, and I can see I'm going to have to break open both of those lone electron pairs so that I have 6 electrons available singly, so they can form 6 single bonds to the 6 fluorines. Now xenon starts with 8 outer electrons, and we can see it really doesn't want to bond. To bring in those 4 fluorines, I'm going to have to break open 2 of those lone pairs. Chlorine trifluoride, chlorine's my central element, and I see I have to break open 1 of those non-bonding electron pairs so that I have 3 free electrons to form the 3 covalent bonds. Okay, now let's predict some geometries, and for this ion we want to know if this is an AX2E, E2, E3, just what is it? Well, we can quickly and easily do this by identifying that the central element is going to be iodine. Let's give it that extra electron that we see for the negative charge, so it has 8 outer electrons. 2 are being used to bond to the 2 bromines, which leaves 6 that aren't. 6 electrons is 3 pairs, and hence this is an AX2E3 geometry. We can quickly see that there's 5 regions of electrons around the central element, 2 X's and 3 E's, or 2 atoms and 3 electron pairs for 5 regions. And so that means at the heart of this we have the trigonal bipyramid. Let's bring our 2 hands together, and then the non-bonding electrons take position up in the equatorial plane, so let's take those away. That leaves the 2 coming out opposite poles, and that gives us a linear shape. The linear shape would be symmetric. Okay, in radon tetrafluoride, we have AX4. Do we have any E's? Yes, radon has 8 outer electrons, 4 are being used to bond, so that's 4 that aren't. And hence an AX4E2 geometry. Okay, so at the heart of this we have the octahedron. The 2 electron pairs are just going to take up position out opposite ends. Think of that being out the top and out the bottom. That leaves those 4 fluorines in the plane. So that would be a square planar shape. Okay, in sulfur dioxide, what should I suspect? Resonance. So I really need to draw 1. And here's 1. And now I can see from my structure that I have an AX2E geometry. And this also points out, if you're having a hard time with any of these, draw them. Might take a little bit more time, but the answer may be more revealing. Okay, so again we have an AX2E geometry, 3 regions of electrons around this, gives us a triangular planar shape, but one of them we don't see, which leaves us with a bent or angular shape. And selenium tetrachloride, selenium is the central element, and how many outer electrons does selenium have? 6. 4 are being used to bond, so that's 2 that aren't. So 1 non-bonding pair for an AX4E geometry. Okay, there's 5 regions of electrons around that central element, so let's bring our 3 fingers on our 2 hands together to form that triangular bipyramid. So again, I got thumb to thumb, forefinger to forefinger, index finger to index finger. And now, where does that electron pair take its position? Once again, it's in the equatorial plane. So let's take away the one with our 4 fingers, and now we have 2 coming out the poles, 2 within the equatorial plane. Let's shake our hands back and forth to remind us that this shape is seesaw. In phosphorus pentachloride, phosphorus is the central element. Phosphorus has 5 outer electrons, and it's going to use all 5 to bond to the 5 chlorines, and hence we have an AX5 geometry. And here we have the true trigonal bipyramid. Okay, predict the geometry of krypton difluoride. Well, I see AX2, and I'm pretty sure there's some E's. So how many E's? I need to know how many regions of electrons are around this central element before I can start predicting its shape. Okay, well, krypton's a central element, has 8 outer electrons, 2 are being used to bond, so that's 6 that aren't, so that's 3 electrons pairs. So that's an AX2E3 geometry. So that's 5 regions of electrons. Let's bring our hands together. And then the 3 electron pairs take position up in the equatorial plane. That leaves the 2 X's, the 2 fluorines, coming out opposite poles, which is a linear shape. In sulfur hexafluoride, sulfur's our central element, has 6 outer electrons. All 6 are being used to bond, so there's just those 6 fluorines for an AX6 geometry. All these are atoms, and so that's the octahedral. In bromine trichloride, bromine's the central element. It has 7 outer electrons. 3 are being used to bond. That's 4 that aren't. So that's 2 electron pairs. For an AX3E2 geometry, I see 5 regions of electrons. Let me put my hands together again. And whenever I have 5 regions of electrons, I'm doing the thumb to thumb, forefinger to forefinger, index finger to index finger, and I see my triangular bipyramid. And then the 2 non-bonding electrons take position up in the equatorial plane. So now I have 1 coming out each pole, 1 out the side for a T shape. Okay, next we have the sulfide ion. Now what should I be suspecting? Resonance. So I need to draw 1. I really only need 1. And now I can see I have an AX3E. And once you draw it, you can see it right there. 3 atoms, only 1 non-bonding pair of electrons, so AX3E. So at the heart of this, I have 4 regional electrons, so there's that tetrahedral. Let me take away one of those bonds, and I see that I have a triangular pyramid shape. For the thiocyanate ion, that's the name of this ion, carbon is the central element, 4 outer electrons, and it's going to use all 4 electrons, and so I don't have any non-bonding electrons around that central carbon. I probably didn't have to draw it to tell that, but with a draw I can quickly and easily see an AX2 geometry. I see a linear shape right there in the structure. Okay, now we're going to determine whether the following are polar, excuse me, or nonpolar. Okay, well, I need to determine AX2E what, so I have some way to tell what the shape is. Well, first, are there polar bonds? That's the easy one to spot. Then, iodine is the central element, 7 outer electrons. Let's give it the extra electron for the negative charge, for 8. 2 are being used to bond, so that's 6 that aren't, for an AX2E3 geometry. So again, iodine had 8 outer electrons around it by giving it the extra electron. 2 are being used to bond, so 6 aren't bonding. 6 electrons is 3 pairs for an AX2E3 geometry. Now let's put our hands together. This is the 5 regions of electrons to start with the trigonal bipyramid. And then the non-bonding electrons come away from the equatorial plane, leaving the 2 bromines coming out opposite ends. In other words, I have a linear molecule here. Now, is that symmetric or asymmetric? It's symmetric. And if it's symmetric, our molecule is non-polar. Remember, we have to have an asymmetric shape. Remember, to be polar, one side looks different from the other. It has to be asymmetric and has to have polar bonds. Polar bonds, easy to spot. The shape takes a little bit more. Okay, in radon tetrafluoride, we have polar bonds. Again, you have 2 different elements, you got polar bonds. Okay, radon's essential element. Radon has how many outer electrons? 8. How many are being used to bond? 4. How many are left over? 4. How many pairs is that? 2. So AX4E2. We have the octahedral, and the 2 electron pairs just come out opposite ends. Let's have one out the top, one out the bottom, and that leaves us with a square planar shape, which is symmetric. And it doesn't matter how you slice and dice it, if it's symmetric, it's non-polar. Now, these 2 are the 2 examples where you do have non-bonding electrons and yet a symmetric shape. With the exception of this AX2E3 and the AX4E2 geometry, every other instance when you have non-bonding electrons, it's going to be asymmetric. So an AX2E2 is asymmetric. AX3E is symmetric. AX3E2 is symmetric. AX5E, is asymmetric. AX5E is asymmetric. So again, these are the only times you have electrons and it is symmetric. Every other time you have a non-bonding pair of electrons, it's going to be asymmetric. Okay, we suspect what with sulfur dioxide? Resonance. Well, first we have polar bonds, and I got to draw one of these since I suspect resonance. And yes, I do see a non-bonding pair of electrons, and like I said, with the exception of the AX2E3 and the AX4E2, if I see a non-bonding pair of electrons, I know it's an asymmetric shape. And the bent shape is indeed asymmetric, which is required to be polar. So I think I may have said something wrong earlier. Let me just clear it up again. AX2E3 and AX4E2. That was our first 2 examples. Those are the only 2 examples where you have non-bonding electrons and a symmetric shape. Every other instance when you have non-bonding electrons, it gives you an asymmetric shape. Okay, in selenium tetrachloride we have polar bonds. Selenium's essential element, 6 outer electrons, so that means 2 that aren't bonding for an AX4E geometry. And like I said earlier, this is anytime you have electron pairs, that's not an AX2E3 or AX4E2, we know it's asymmetric. This actually happens to be the seesaw shape, which is asymmetric. And hence selenium tetrachloride is a polar molecule. Okay, in phosphorus pentachloride we have polar bonds. Phosphorus is an essential element. It has 5 outer electrons. All 5 are being used to bond, so we don't have any non-bonding pairs. Now do note at this point, it's clear that we only have one attachment on our central element. We only have one thing, those chlorines. And if you only have one thing attached, then we know that this is symmetric. Again, one thing attached, only one thing attached. It's always going to be symmetric. And symmetric always equals non-polar. Okay, now that I've gotten you warmed up, I recommend that you do some on your own. So why don't you pause this and come up with your own answer? Okay, krypton difluoride. Do we have polar bonds? Check. Do we have an asymmetric shape? Well, krypton's our essential element. It has 8 outer electrons. 2 are being used to bond, so that's 6 that aren't bonding for an AX2E3 geometry. I have 5 regions of electrons around my essential element, so let me put my 2 hands together, one over the other. Again, index finger to index finger, forefinger to forefinger, thumb to thumb. And now where do those 3 non-bonding electrons take position? In the equatorial plane, which leaves those 2 fluorines coming out opposite ends. Remember, the AX2E3 geometry was one of the 2 that had non-bonding electrons and yet was symmetric. And if it's symmetric, it doesn't matter how polar the bonds are. The molecule is non-polar because the symmetry cancels the pull in each direction. Sulfur hexafluoride has polar bonds. Check. Does it have an asymmetric shape? Well, sulfur's essential element. Sulfur has 6 outer electrons. All 6 are being used to bond. So no non-bonding pairs. So all I see is fluorines attached to that sulfur. So what does that mean if you have only one thing attached to your essential element? That it's symmetric. In this case, it's a symmetric octahedron. But only one thing attached, it's always symmetric, and symmetric always means non-polar. Next, we have bromine trichloride. Do we have polar bonds? Check. That's the easy one to spot. 2 different elements, meaning we have a compound and not just an element. We have polar bonds. Then, bromine's essential element has 7 outer electrons. 3 are being used to bond, so that's 4 that aren't. So an AX3E2 geometry. Again, 4 electrons is 2 pairs. 5 regions of electrons. Let me put my hands together. The 2 electron pairs take position up in the equatorial plane. That leaves 1 in the equatorial plane and 1 out each pole, which is a T shape. Is this one of those symmetric shapes? No. Again, with the exception of an AX2E3 and an AX4E2, anytime you have non-bonding electrons on your essential element, suspect asymmetric molecule. Okay, for the sulfide ion, I do see polar bonds, and I suspect, and I hope you suspect, resonance. So I need to draw one. Drawing one, I see I have an AX3E geometry. This is one of those with electron pairs. That's not an AX2E3 or AX4E2, so it's not one of our 2 symmetric. It's a triangular pyramid shape, which is asymmetric, and hence the sulfide ion is polar. For the thiocyanate ion, I see 3 different elements, so I know I have polar bonds. And I'm not sure I even need to draw it, but once I draw it, I can see that left end doesn't look like the right end. I have an AX2 geometry, which is linear. And if the 2 guys on each of the end were the same, so those 2 sulfurs or 2 nitrogens, then it would be symmetric. But because the sulfur and the nitrogen are 2 different things, remember, when you bring in a second thing, with the exception of an AX2E3 and an AX4E2 geometry, that second thing ruptures your geometry, so that is asymmetric. And I hope you can see by just looking at that molecule that it's going to be polar. Okay, on to atomic orbital hybridization, and we have hybridization of our atomic orbitals. So remember those atomic orbitals, the S's, P's, D's, and F's. For right now, we'll talk about S's, P's, and D's. F's aren't going to come into it too often. But we tend to need to hybridize these atomic orbitals when either they don't have a shape that's conducive to forming a bond between the 2 atoms, or they're orbitals are filled in such a way that they're not available for bonding. Now, the theory states that, and no, when we draw a molecule, using our normal procedure, you draw on your central element, and the non-bonding electrons are the ones that form bonds. And so when I would draw in nitrogen, those 3 electrons that are not paired, I know when to form pairs and tell me I want to form 3 bonds, for example. So normally we just say the number of unpaired electrons would be equal to the number of bonds formed. I mean, that actually is still true, but if we simply just look at the electron configuration and subshell notation, we may find that we actually don't have the number of unpaired electrons that we would think that we have. Let me go ahead and give you an illustration of this, and then we'll talk more about hybridization. Now, there are very few molecules that have no hybridization at all. The hydrogen molecule is pretty much the only one that doesn't need any hybridization at all. First, if we had an isolated hydrogen atom, we have 1 electron in its 1s orbital, and it's just ready to accept another electron, to pair up with another electron, and essentially fill that orbital. So again, do note that 1s orbital has 1 electron in an individual hydrogen atom, and it's going to gain an additional electron when it pairs up to form that covalent bond. And now we have the 2 electrons that hydrogen wants. Now, the shape of that orbital, nice and spherical, is not too tough to essentially elongate, to essentially get the main concentration of electron density between the 2 atoms. Now, when we would have a chlorine atom react, well, do note, here's the orbital box diagram for a chlorine atom. I can see that free non-bonding electron telling me that chlorine wants to bond once, it wants to pair up with somebody's electron, and at that point I've satisfied its octet. Now here we would have to do quite a bit to elongate or to adjust the size of that p orbital. Remember, a p orbital has 2 lobes. We're going to have to do something with that to essentially get it to force the majority of the electron density between the 2 atoms. But let me just go ahead and say one thing, and that is we're going to consider these 2 examples don't need to hybridize their atomic orbitals. Even though, to be honest with you, especially for the p's, they are going to hybridize a little bit, but not in the same fashion as we're going to talk about when we need to satisfy our bonding potential by donating electrons from filled orbitals to unfilled orbitals. A good example of this is the carbon atom. So here is an example of the carbon atom's orbital box diagram. So there's the orbital box diagram for carbon. Now, if we just went with the theory I just said, we would ask and answer, how many unpaired electrons do we have here? 2. So how many bonds would carbon form? 2. But we know that's not correct. How many bonds does carbon want to form? Well, as many as it takes to get it to the next noble gas, neon, which means it needs to form 4 bonds. And we know that carbon indeed does form 4 bonds. How can it do so with this orbital arrangement? Well, actually, it's going to hybridize. This is really what we're going to see when we're talking about hybridization. We're going to donate one of the electrons from a filled orbital, that 2s, to an empty orbital, one of those 2p's. Do note that's changing one of those black arrows into a red arrow, and now we can see 1, 2, 3, 4 unpaired electrons, and then the 4 blue ones came and paired up with it, forming the 4 covalent bonds. So this is an excellent example of orbital hybridization. We just didn't have the bonding potential that we should have and needed to have by not donating that electron from the 2s out to the 2p. So for our conversation about orbital hybridization, it's all going to be about bonding needs, bonding potential. Now, eventually, we may even bring in the d orbitals. Whenever we're dealing with an expanded octet, where are those additional electrons going to go? Well, let's just go ahead and look at the phosphorus atom. And here's the orbital box diagram for a neutral phosphorus atom, meaning it's all by itself. And we can see the 3 unpaired electrons in the 3p subshell telling us it wants to form 3 bonds. And indeed, phosphorus does want to form 3 bonds. But we've seen instances, like in phosphorus pentafluoride, where it is forced to bond with two additional times. And how can it bond 2 additional times? Well, you've seen this before. We take one of those pairs and break it open. And so here we can see what happened when we broke open that pair. We now had a single electron in that 3s, and now a single electron in the 3d, and at that point we have 5 free electrons, which can then form 5 covalent bonds. And there's the 10 regions of electrons, the expanded octet. But we can see it visually here in this orbital box diagram. Okay, let's look at the sulfur atom. There's the orbital box diagram for the sulfur atom. We see the 2 unshared pairs in the 3p, so we already are thinking it wants to form 2 bonds. But we've seen fluorine force it to open up both of the non-bonding pairs. That would be the 3s, and one of those 3p orbitals. So essentially we're going to donate 1 from each of those out to the 3D, and then I hope you can see, just counting the 4 black and the 2 red, that we have 6 electrons individually now, and then they can form 6 bonds. Remember, the blue arrows pointing down are the donated bond, or the additional electron in the bond that we get from the peripheral atom. Okay, so this is where we really need to hybridize our central element so that we have the bonding potential to match our bonding needs. Now, ultimately, the hybridization, I'm going to go over the different types of hybridization in their nomenclature, but I want to go ahead and point out that if you look at these pictures, you can see that the type of hybridization is going to depend on the orbital box diagram of the atom all by itself, but it's also going to depend on the number of shared pairs, but also the number of non-shared pairs. Let me just go ahead and give you the real skinny. What it depends on is the total number of regions of electrons around your central element. But I hope you can look at these illustrations and see what hybridization I needed for that sulfur hexafluoride depended on how many shared pairs did I have and how many unshared pairs did I have. We'll talk about that more here in a second. Now, to get this orbital hybridization, we're going to essentially do what's called mixing of orbitals, and that gives us these hybrids. Essentially, we get something that's kind of an intermediate between an S and a P and a D. Well, sometimes a D, depending on you need a D. Let's start simple. Let's keep it with the S's and the P's. Okay, so do note these 5 different designations for these orbital hybridizations. SP, SP2, SP3, SP3D, SP3D2. What does that mean? Well, do note that if we have an S orbital and we donate an electron into the p orbital, so essentially now we're dealing with an atom that has an s orbital that was changed and a p orbital that was changed. Well, essentially now we have 2 hybrid orbitals, and we would call these sp. When you look at that s and p, look at that as 2 orbitals for 2 regions of electrons. Now, if we ended up with an S and 2 P's, we would have what's called an sp2 orbital. So again, we would have an s and two p's for a total of 3 orbitals. And again, these will be called sp2. Let's look at that sp2. S, that's 1. P2, that's 2 more, for a total of 3 orbitals. So sp, I hope you can see that's 2 orbitals. sp2, I hope you can see that's 3 orbitals. Now if I'm mixing my s's and 3 p's, then I have 4 regions of electrons around my central element, giving me what is called an sp3 hybrid. So again, sp, I see s and p, 2 orbitals. sp2, that's like spp, 3 orbitals. sp3, 1 s and 3 p's for 4 orbitals. And if I bring in my d's, I'll have an sp3d, that'll be 5 orbitals. sp3d2, which will be 6 orbitals, and we'll talk about that in just a second. Now, I need to go ahead and mention that if we end up with multiple bonds, those aren't going to add to our number of hybrid orbitals. It turns out that the p orbital, and normally we're going to find it, it's right there waiting for this, that a p orbital is in a perfect orientation to form a multiple bond. Because the first bond occurs between the 2 atoms, any additional bonds are going around the atom. So think of above and below, or to the left and to the right. And a p orbital is going to bend around and give us that orientation. I have a picture coming up here pretty soon, but just keep that in mind. The p orbital with its 2 lobes is going to be in a good position to form the multiple bonds, meaning the second bond and a double bond, or the second and third bond and a triple bond. Okay, let me just summarize some of this and then I'll give the illustration. Okay, if we have 2 regions of electrons, then we're mixing an s and a p orbital for an sp hybrid. And with just 2 regions of electrons, we should suspect a linear orientation. We've seen how carbon dioxide is linear, 2 regions of electrons, AX2. Beryllium difluoride is linear, AX2. So again, I hope we can see 2 regions of electrons, and they're both atoms, AX2. Okay, for 3 regions of electrons, we're going to need 3 orbitals to accommodate them, and so we're mixing 3, so that's an s and 2 p's, and that gives us what's called an sp2. So again, look at the s is 1, the p2 is 2 more for 3 orbitals. And if there is 3 atoms in those 3 regions of electrons, then, being as far away from each other as possible, we get that triangular planar shape. And we saw that with the boron trifluoride, and I believe we also saw that for sulfur trioxide. Now, if we have 4 regions of electrons, then we're mixing 4 orbitals, so an s and 3 p. So sp3 is what this hybrid is called. And when I have 4 regions of electrons around my central element, I have the true tetrahedron. And when I would look at a molecule of methane, CH4, I see that true tetrahedron. But ammonia still has that tetrahedral shape at the heart of it. We just don't see the bond that would go up. We see the result, which is that triangular planar shape. And the same with water. Remember, at the heart of these molecules that have 4 regions of electrons, we have the tetrahedron. Just like at the heart of any molecule that has 3 regions would be the triangular planar shape. And let's go on to 5. The heart of anybody with 5 regions of electrons is going to be that triangular bipyramid. Remember how we bring our 2 hands together. And anybody with 6 regions at its heart is going to have the octahedral at its heart. Okay, let's go back to 5 regions of electrons. So we need 5 orbitals. We're mixing an s. 3 of those p's. We're up to 4. I need 1 more, so I bring in a d. So this is called sp3d. So s, there's 1. D, there's 1. p3, there's 3, which adds to 5. Remember, when we have 5 regions of electrons, at the heart is the triangular bipyramid. Even if one of them is a non-bonding pair of electrons, And we have the seesaw. 2 of them might be non-bonding electrons, T-shape. Or 3 may be non-bonding electrons for linear, but at the heart of it is still that triangular bipyramid. And 6, we need 6 orbitals to accommodate the 6 regions of electrons. So I have my S, my 3 P's, that's 4. This time I'm going to need 2 D's. I hope you can count them and see that we have 6 orbitals mixed to give us 6 hybrid orbitals, and that's the type of orbital when we have 6 of them. And at the heart of this is the octahedron. So in sulfur hexafluoride, we can see that true octahedron. In the chlorine pentafluoride, we have 1 non-bonded pair. So that's an AX5E. So that's the square pyramid shape, but still at the heart of it is the octahedron. Same with the xenon tetrafluoride. Okay, so that's essentially it on why we need to hybridize atomic orbitals for molecular orbitals. And what's the designation of this orbital based on, well, it's orbital hybridization, and again, it's based on how many regions of electrons do you have around your central element. Got to be at least 2, sp, 3 sp2, 4 sp3, 5 sp3, being in a d, 6 sp3, bring in 2 ds. Hope that makes sense. Just like anything else, practice goes a long ways. Okay, let's go through an example. Give the hybridization of carbon and carbon tetrafluoride. Okay, well, let's see. Carbon has 4 outer electrons. All 4 are going to be used to bond. So I've got 4 orbitals. So sp3. So again, 4 regions means 4 orbitals. So I need a mix 4 atomic orbitals. Okay, for phosphorus and phosphorus trifluoride, well, phosphorus has 5 outer electrons, 3 are being used to bond, so that's 1 non-bonding pair. So this will be an AX3E. The 3 and the 1E adds to 4 regions of electrons. So that also would be sp3. Make it clear. Carbon tetrafluoride was sp3. Is that 4 regions of electrons? Phosphorus trifluoride is sp3 because it also has 4 regions of electrons. It just happened to have one of them be a non-bonding pair. So I hope that makes it clear. It doesn't matter if they're bonding or non-bonding. It's about how many regions of electrons are around that central element. Okay, how many regions of electrons are around the sulfur and sulfur tetrafluoride? How many outer electrons does sulfur have? 6. How many are being used to bond with 4 fluorines? 4. So that's 2 that aren't, for 1 non-bonded pair. So this is an AX4E. That's 5 regions of electrons. To accommodate the 5th, we have to bring in a D. So sp3D. Okay, the last thing that we need to go over before we just do a lot of practice is sigma and pi bonds. I hope that you will find this to be an easy concept. I think you will. Where, let me give you kind of the long way to it, and then I'll just give you the real skinny. Sigma bonds are essentially the bond that results from concentrating the electron density between the 2 atoms. So I've got 2 atoms, and I'm concentrating electron density between them. That is my sigma bond. Ultimately, if I'm concentrating the electrons between 2 atoms, I'm talking about a single bond. So the sigma bond consists of the electron pair, one from each of the 2 atoms donating them. And so the sigma bond consists of those 2 atoms from those 2 sigma bonding orbitals. And again, ultimately a sigma bond is a single bond. Then we have pi bonding orbitals, and as I mentioned, for the p orbitals, these are in perfect orientation to to stick out above and below the molecule, so not between the two atoms, and then kind of bend around. And as they bend around, they finish forming the bond. So actually, a pi bond has two lobes of electron density, one above the plane of the molecule and one below, or maybe say one above the axes and one below. We could have it just as much to the left and to the right, but let me keep it simple for right now. Just think of one above and one below. And a pi bond is then going to be the additional bonds beyond a single bond. So for example, single bond, sigma. But if I have a double bond, the first in that bond is a sigma, that second bond is a pi. And if I had a triple bond, then the first is a sigma, and the second and third bonds would be pi's. Let me give you some illustrations. Okay, on the left we have ethene, sometimes called ethylene. And we have a double bond between the two carbons. Do note, if I would draw this, I would see I would have a double bond between my two carbons. We've actually drawn this before. Now, let's forget about that second bond. Where is that first bond? Well, that first bond, as a bond between the two, is a sigma. Do note the bonds of the hydrogens are also sigmas. They're all single bonds. Now let me complete my second bond. Well, those electrons have to go somewhere, and the electron density, or the region between the two carbons, is already filled. So I need to bring one above and one below the plane of the molecule. And that here actually is a visual representation showing us that pi bond. So here we can see, well, we can just count 1, 2, 3, 4 sigma bonds to the 4 hydrogens, one more between the two carbons, so that's 5. And then one pi bond. We're seeing the pi orbital. That's going to be the two lobes of the pi orbital. That's one pi bond. So again, we have 5 sigma bonds and 1 pi. What about in acetylene, sometimes called ethyne? Here we have a triple bond. So this is the guy on the right. We have a triple bond. Well, let's take away the double of the triple bond, and we would see one bond between the two carbons, that's sigma, and then one above and one below for the second bond between them. And then how about one to the left and one to the right for the third bond between them? I really wish they would change this picture so you can more clearly see one above and one below, and one to the left and one to the right. But if you look at those pairs of arrows, we can see the pair showing that one on the top and the back is pairing up with the one on the bottom and the front. And the one on the top front is pairing with the one on the back right. So again, you can see that kind of looks like a V. It's showing you which ones are which. Okay, so again, the one between the two atoms, you can think of that if it was a single bond as a sigma, or the first of a multiple bond as a sigma. Any additional bonds are pi's. So in ethylene, I have one double bond, so that's one pi bond. And acetylene, I have two bonds. I have a triple bond, so that's two additional bonds, so two pi bonds. And I hope you can see how the p orbitals were in an excellent position to form the pi bonds. And that's why we didn't need to hybridize them. Now, they actually did change somewhat. So to be honest with you, there is some hybridization, but it's not the same hybridization like we had in these other instances where we're mixing electrons by donating them from one filled orbital to an empty orbital. Okay, nice and simply, to find the number of sigma and pi bonds in your example, if all else fails, draw it out, and any single bonds are sigmas. If there is a multiple bond, the first in that bond is a sigma, any additional bonds are pi's. And again, the double bond has one pi, a triple bond has two pi's.
So you might think of a triple bond as having one sigma between the two, one above and below for one pi, one to the left and one to the right for a second pi. Okay, get the number of sigma and pi bonds in nitrogen. Well, there's a triple bond between those two nitrogens. So how many sigmas? 1. How many pi's? 2. In carbon dioxide, when in doubt, draw it. And that makes the answer just jump right out there. How many sigmas do you see? I hope it's 2. And how many pi's do you see? And again, I hope it's 2. There's that acetylene. Let's go ahead and draw it by hand where we can see that double bond between carbons. How many sigmas do you count? I count 5. 4 to the 4 hydrogens and 1 between the 2 carbons. And then how many pi's? 1. The double bond would have one bond, one pi bond extending above and below the plane of the molecule. Okay, let's practice some of the things that we've just learned. For the following, give the orbital hybridization for the central element. Give the number of sigma and pi bonds for the entire molecule. And I can't stress enough, if you have any difficulties, draw these. Now, you don't always have to draw them, but when in doubt, draw it, because it's actually going to be much easier if you draw one. Okay, and here is carbon tetrachloride. So I do my normal procedure, and it's easy to see 4 sigmas and 0 pi's. And the orbital hybridization, well, how many regions of electrons do you count? 4. So I need to bring in an S and a P and another P and another P for an sp3. Again, that was 4 sigmas and 0 pi's. For carbon disulfide, carbon is our central element. Let's bring in our 2 sulfurs. We have leftover electrons. So here's my structure. And now I can see 2 regions of electrons around my central element. So what's the hybridization? sp. How many sigmas do you count? 2. How many pi's do you count? 2. There's acetylene. Never hurts to draw it. Step 1. Step 2. Step 3. And now, how many regions of electrons are around each carbon? 2. So what's the orbital hybridization? Well, how many orbitals does it take for 2 regions of electrons? 2. And the orbital hybridization when there's just 2? S and P. And now, how many sigmas do you count? 1, 2, 3. How many pi's? 1, 2. Okay, here's hydrazine, and step 1, step 2, step 3. And I think once I've drawn this, the answer should just drop out at you. How many regions of electrons are around each nitrogen? I hope you said 3. So what's our orbital hybridization? I hope you said sp2. And how many sigmas do you count? I hope you count 3. And how many pi's do you count? I hope you count 1. So again, each nitrogen had 3 regions of electrons around it, so we had a mixed 3 orbital, a S, a P, and a P. So sp2. The first electron in a multiple bond is a sigma, so I hope you can see where there's just 3 sigmas, and any additional would be a pi. Same question for sulfur hexafluoride. Well, let me go ahead and draw one. Step 1. Step 2. How many regions of electrons are around that central element? 6. How many orbitals does it take to mix? For 6 regions, 6. And what's the orbital hybridization? S and P and P and P and D and D. So sp3, D2. How many sigmas do you have? 6 single bonds, so 6. No multiple bonds, so no pi. Okay, xenon tetrafluoride. Xenon's a center element. So in drawing it, step 1. We break open 2 of those non-bonded pairs so I can bring in my 4 fluorines. There's step 2. No leftover electrons, meaning leftover single electrons, so there's no step 3 here. Okay, I can see how many regions of electrons are around that center element. 1, 2, 3, 4, 5, 6. So our orbital hybridization, sp3, d2. How many sigmas? 4 single bonds. How many pi's? 0 multiple bonds. And chlorine trifluoride. Chlorine's a central element. I need to break open one of those free electron pairs to bring in my 2nd and 3rd fluorine. At this point, I can see I have 5 regions of electrons around my central element. So what's my orbital hybridization if I have 5 regions? I need to bring in an S, a P, a P, a P, and a D. And 3 single bonds for 3 sigmas. Same question, same approach. Iodine is our central element. I have to break open 2 of those non-bonding pairs so I can bring in my 5 fluorines. How many regions of electrons do you count? I count 6. So what's our orbital hybridization? sp3d. How many sigmas? 5. Oh, I think I forgot I think I counted wrong. Not 5 regions, 6 regions. So sppdd for sp3d2. Okay, for selenium tetrachloride. Selenium's the central element. Need to break open one of those non-bonding pairs of electrons to accommodate the 4 chlorines. This time I'll double check 1, 2, 3, 4, 5. Yep, 5 regions of electrons. So S and P and P and P and 1D for sp3d. And those 4 single bonds mean 4 sigmas. Bromine trichloride. Bromine's the central element. We break open one of those non-bonding pairs so I can bond to my 3 chlorines. 1, 2, 3, 4, 5 regions of electrons again. So again, sp3d. This time we have 3 single bonds. So 3 sigmas. Okay, same question, this time for nitrosyl chloride, and I suspect, and I hope that you suspect, resonance. So, in an attempt to draw my first resonance structure, what I'm going to do is, I'm going to draw my nitrogen, oxygen to the left, oxygen to the top, chlorine to the right. Of course, I could just put it in some other order. Then, we saw before that the chlorine wasn't going to participate in resonance, so let's just count it's 1 electron that's going to put into a bond. So there's 1 from chlorine, 5 from nitrogen, 6 from each oxygen for a total of 18 electrons, which is 9 pairs. So I put 1 pair between the nitrogen and each oxygen. and the chlorine, so one between the nitrogen and the oxygen on the left, one between nitrogen and the oxygen on top, one between nitrogen and the chlorine on the right. Then, so that's 3. Our 4th, 5th, and 6th pairs of electrons I would give to the oxygen on the left. Our 7th, 8th, and 9th pairs of electrons I give to the oxygen on top. So that's what I've done so far. And do not, that's not one of our resonance structures. Our nitrogen doesn't have 4 electron pairs or 8 outer electrons. But we know what we need to do. We need to bring down one of those free electron pairs from one of those oxygens. And it doesn't matter if it's the one on the top or the one on the left. Either way, how many regions of electrons are around the central element? 3. So we're mixing 3 orbitals, spp or sp2. And we can see clearly how many sigmas? I count 3. How many pi's? I count 1. So again, 3 regions of electrons, 3 orbitals, sp2, 2 single bonds, and 1 multiple bond is 3 sigmas. That second of the double bond is a pi. Okay, I'll give you a moment to draw dinitrogen oxide. We might start like this. Again, I'm going to lump all the electrons together. We've got 16 outer electrons for 8 pairs. And I just randomly chose who got pairs and who didn't. Didn't really follow any particular prim scheme. And now that I've drawn this, let me start moving some of those electrons around so that I can form a resonance structure, meaning form a compound that actually has 8 electrons around each element. Here will be 1. Here's another. And you may recall the 3rd as well. Now I didn't have to draw them all. Why don't I have to draw them all? Because they all have the same orientation. They all have the same hybridization, the same geometry, because that central element has the same number of regions of electrons around it. The one on the left we see 2 regions, the one in the middle we see 2 regions, the one on the right we see 2 regions. We might call these all AX2, but for right now what we need to know is 2 regions. So how many orbitals need to be mixed to accommodate 2 regions? And I hope you got 2. So an S and a P. And when we count sigmas, in each of these I count 2 sigmas. And when we count pi's, in each of these I count 2 pi's. That may seem strange that we're going to have the same orbital hybridization, same number of sigmas, and same number of pi's for anybody participating in a resonance structure. In a way that should make sense, because remember, we can't really change the geometry of the atoms. That would just take too long. Yes, atoms are such small things that they can move tremendously fast, but electrons are tremendously smaller and can move tremendously faster. Okay, same question, same approach, and I suspect resonance with sulfur trioxide. I would begin by putting my sulfur in the middle, and the oxygen on the left, 1 on the right, 1 on the top. Count a total of 24 outer electrons, just 12 pairs. Start by putting 1 pair between the sulfur and each of those 3 oxygens, so there's 3. Then 4, 5, and 6 go to the oxygen on the left. 7, 8, and 9. Actually, 4, 5, and 6 go to the oxygen on the left. 7, 8, and 9 will go to the oxygen on the top. 11 and 12 can go to the one on the right. And then we see that the sulfur still needs an additional electron pair. And so we'll bring down one of those free electron pairs from one of those 3 sulfurs. Again, I don't have to draw all of them because one tells me what I need to know. What's your orbital hybridization here? sp2, 3 regions of electrons around that central sulfur. How many sigmas? 3. How many pi's? 1. And again, I didn't have to draw the other resonance structures to see that they also would be identical. The nitride ion, I'm just going to go ahead and draw one. Yes, I could have drawn it in a different fashion, but in either way, we have an AX2E for 3 regions of electrons. So again, it's going to be sp2. I count 2 sigmas this time and 1 pi. I want to take a few moments and draw at least one resonance structure of the nitrate ion. And I'm pretty sure once you do your orbital hybridization, your sigmas and pi's will just fall into your lap. And I imagine you got something that was like this. Didn't matter if the double bond went to the option on the left or on the right or on the top. And we can see how many regions of electrons around the central element? 3. So again, sp2. I hope you count 3 sigmas and 1 pi. One more, we have the hydrogen carbonate ion. And you may recall the way that I drew these. I hope that you have at least some way that will reproduce this for you. But once I have one structure, I can see the carbon has 3 regions of electrons around it. So that's one more time, 3 regions, so one more time, sp2. And I count 1, 2, 3, 4 sigmas and 1 pi. Don't forget to count that first bond and a multiple bond as a sigma. Okay, that concludes 7.4, and hence that concludes chapter 7. And the last thing that we talked about was atomic orbital hybridization. Atomic orbitals are great for atoms, but when we try to bring them in to form molecules, we often need to change their orientation somewhat. I mean, change their, well, just that, their orientation, their shape. And if we have more bonding needs than our bonding potential, meaning we need to donate electrons from filled orbitals up to empty orbitals. Remember carbon? That definitely says we need to hybridize our atomic orbitals to facilitate molecular orbitals. So again, these are often called molecular orbital hybrids. Okay, we saw how those were hybridized, and remember, to determine the hybrid, you count how many regions of electrons are around your central element, and how many regions is how many orbitals you have. How many orbitals you have is the same as the number of orbitals that you mixed. So if I have 2 regions, 2 orbitals, an s and a p. 3, need to bring in a third, another p. 4th, we need to bring in another one, another p. So that would be sp3. If I go beyond 4 regions, I'm going to start bringing in my Ds. So 5 regions would be sp3d, 5 would be sp3d2. And then for sigmas, hope you found that to be an easy concept. Sigmas is simply the number of single bonds, and count the first bond and the multiple bond as a sigma. Any additional bonds beyond that are deemed pi bonds. Okay, and again, that concludes chapter 7.